Okay, part 2, pulse code modulation. I'm looking at the last bits and looking at some example questions. So far we've looked at everything, and the low pass filter cuts off the high frequencies to avoid aliasing. Remember that the information signal doubled, Nyquist theorem, must be less than the sampling clock frequency. That's the first thing we need to remember. If doubled is not less than the sampling clock frequency, then we need to work out the difference to work out the output frequency, not the information signal frequency. The other relationship we need to memorize between the different parts is if we take the sampling clock frequency and times it by n, the number of bits, that's got to be less than the piezo clock frequency. So you need to remember those details between the different bits. And the piezo clock frequency is the same as the CPO clock frequency, as they're both shift registers. The Schmidt trigger is cleaning up the noise from the signal from the transmission. The ADC is converting from analog into digital. And what do the DAC and the low pass filter at the end do? Well, the DAC converts the digital signal from zeros and ones back into analog voltage values, and the low pass filter smooths it out a bit. It's not perfect, but it does a pretty good job, because remember, a low pass filter has that kind of curve on it for the different frequency levels. So then we'll add that curve, which will help us smooth things out. Let's have a look at a couple of example questions. I would recommend that you pause the video at this point and have a go at the questions yourself. Okay, let's have a look at them. You would be expected to draw the block diagram from memory or to fill it in, and to draw the circuits for shift registers or Schmidt triggers or ADCs or DACs as part of this chapter. So part A, minimum clock frequencies for both sampling gate clock and piezo clock. Well, we know that the maximum information signal is 4.3 kilohertz. Can't be any bigger than that. So if we double that, we get 8.6 kilohertz. Now our sampling gate clock frequency must be bigger than this 8.6 kilohertz. So let's just round upwards, always round upwards if you're doing this. If you round down, you're not greater than 2 times. So let's say 9 kilohertz. For the piezo clock, we've got to multiply it by the number of bits. So we do 10 lots of 9, which is 90 kilohertz. And this is, let's say this is the piezo clock frequency. Ideally, you're a little bit higher than this, just to be on the safe side, with tolerances of different components and things like that, adding a bit of leeway. So I would say at least 10% over, just to be on the safe side. But let's just say it's 90 for now. Part B, calculate the time needed to transmit a single 10-bit PCM sample. So time is 1 over frequency, so 1 over 90 kilohertz. That's 11.1 recurring microseconds. Now that is the time for every single clock pulse, but every single clock pulse is the time it takes to do 1 bit, not all 10. So we need to multiply this value by 10 to work out the time it takes to get the whole 10-bit sample through. So that's 111 microseconds. You could have done 1 over 90, the sampling gate clock frequency. That would have been fine too. Okay, question 2. Again, I would recommend you pause this video and have a go at it. So first bit, smallest number of bits needed for the ADC to meet the specification. So this is just a recap on what ADCs do. So we know that resolution is equal to voltage range over 2 to the n, where n is the number of bits. And I'm just going to do trial and error. You could use logs, with the 500 microvolts provided, and that would be a little bit quicker. I'm going to start with 2 to the 10. It's my first guess. If I do that, then I get 7.8 millivolts, which isn't good enough. So I go further. I say let's do 2 to the 15. That is 244 microvolts. So that's good enough. So 15 bits would be enough. But we want to minimize the number of bits we use because every bit is expensive. And we need to double the number of comparators in our ADC. So obviously that doubles the price almost. So let's try and get away with less, shall we? So let's try 2 to the 14. That is 488 microvolts, which is still good. So let's improve that. Let's say 2 to the 13. That will be 976 microvolts, which just doesn't work. Each time we get rid of a bit, obviously we double the value because we've got rid of one of those powers 2 in the denominator. So 14 bits are required. Minimum 14. You could have more, though you're not necessarily gaining from having a lot more than the resolution required. Okay, part B. A pan voltage of 1.5 volts is applied to the inputs of the ADC. What's the output? So I've just left a bit of space. So we've got 1.5 volts. We're going to divide it by the 500 microvolts because that's how many steps there are. Each step is 500 microvolts. So that's 3,000. Now that's in decimal. We need to convert 3,000 into binary because an analog to digital converter will convert the analog value of 1.5 volts into a binary value, not into a decimal value. So we need to work out 3,000 in binary. Okay, so that's going to be quite a high value. But remember, we've got 14 bits. So 2 to the 14 is a very big number. 16,384. We don't need any of those. 2 to 13. 8,192. Again, too big, so that's going to be a 0 in that binary value. 2 to the 12. It's 4,096. That's still too big. So we're going to start with 3 zeros. 2 to the 11. I could just halve this. So 2,048. So yes, we do need one of those. So then we do our trick for converting from decimal into binary, where we do our decimal value and we take away the biggest value in binary, and we keep repeating it. So 3,000 minus 2,048. Is 952, still quite a big number. So the next number after that is our tens. So 2 to the 10 is going to be 1,024. 952 is too big for that, so we don't need any of those. 2 to the 9, halving again, so that will be 512. We do need a 512. Just going to put this underneath the space. That's 440. That's still quite a big number. So we do need one of those. Then we do 2 to the 8. It's a slow process, but you do need to be able to do it. Next one is 256. So we need to do 256 from this. $184, 2 to the 7, 128, so we do need one of those. $56, and we don't need a 64. That's our 64s, so we need 128. We don't need a 64. We are going to need a 32. Our next number is 16, so 24 minus 16, we do need a 16. That'll be 8. So our next one is 8, so that's perfect. That gives us 0. We don't need a 4, 2, or 1. So we needed a 16, so that's 2 to the 4. So we do need a 16. We did need an 8. And the 4, 2, and 1 we don't need any of. So sorry, it's got a bit squeezed there. So this would be 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0. So that's the binary output of our 14-bit ADC. You do need to be able to do this even for quite large values. Usually they don't go beyond 8-bit just because of the amount of time this takes. Okay, do make sure that you've gone over the overview and you're really happy particularly with these two diagrams and how the relationships between all of the different blocks.